All right, guys, let's get started. So as you know, we're covering PyTorch, essentially, which is a pretty important framework for deep learning. And we're going to be using PyTorch until the end of the semester. So on Monday, I gave you the first example, the first complete pipeline of using PyTorch with the Iris dataset, and we created a simple multi-layer perceptron, a neural network. Okay, so that, as I've said many times, if there's like one thing you should take away from this class, is like these classes, right? This week and next week, being able to create these networks allows you to solve many problems. Okay, many problems. So my plan today is to continue with PyTorch. We built a multi-layer perceptron. Now we're going to build deep learning, right? So we're going to build a deep neural network, and you'll see that essentially you already know how to build a deep neural network. You've got 80% of the code already, right? So you just need to understand a few of the additional things we have to do. Then after that, I'll probably switch to another data set like the wine quality data set, and we'll cover that. The same thing. We're going to build some networks on a different data set, both for classification and regression. And then finally, not today, but next week probably, we'll look at images. So I'll bring in the MNIST data set, and we're going to build deep neural networks, and we're going to look at something called a CNN. And along the way, we're also going to learn really quickly how to deploy those models using something Onyx, which is pretty easy, actually. So once we do that, you will have a lot of the information you need to start working on the assignment that I'm going to give you, and also phase one of the term project. Okay, so that first presentation is going to be probably in about 2 weeks, or 2 or 3 weeks. So that first, the competition will take place in class on a Wednesday probably. Everyone needs to present their work, and then at the end of class we select the winner, whoever got the best model. All right, so you should have everything, all the code hopefully by the end of next week. All right, and then after that I just have to add the transfer learning part, but that's going to be useful for phase two, those presentations will be the week before final. So that's your term project essentially. Make sense? So each phase will be worth 10% of your grade, because I think the total allocation for the project is 20%. All right, so that's the idea. So let's get to it. So I'm going to click here. A few reminders. One thing. So the exam is next week, but the other section asked me to have the exam on the lab day. So that's like on the Thursday for them. So do you guys have a preference? Do you prefer the exam on Monday or Wednesday? Does it matter? Wednesday? Okay. All right. Good. So so it'll be consistent with the other class then. You'll have exam 2 on the Wednesday. Any questions about that? Remember, it's comprehensive, closed notes, but you're allowed your cheat sheet. You can write whatever you want on it. Okay? All right, great. So a couple of things. Remember, I've given you the notes, so click on this, and you can read through everything that I'm explaining in class, the lectures, everything, all the code is explained here, so make sure you read through this material, okay? And then today, I'm just going to focus. I've explained, that's the great thing about this, right? So the first day, I had to explain literally like every line of code. But now I don't have to do that. We're using the same code to solve different problems. And so I don't have to explain every line anymore, right? All right, so let's click on Repo Torch. So this is where our code lives. We're going to be using Colab. So these are the scripts. Currently we're using the Iris data set, and we're doing classification with the Iris data set. So I'm just going to take this code again that we started on Monday, and I'm just going to use a different neural network architecture. And that'll be it as far as that, so that we can compare. After that, we'll switch to these two, which have to do with a different data set. We'll use the wine quality data set for both the classification problem and the regression problem. And as you can see also, it'll have the XGBoost. The XGBoost part is just like 10 lines of code. So it's really something, it's a function, you grab the model, you run it through the function, and now you have an external file that you can upload to the GitHub pages, to your website, right? And you can access this file via JavaScript, for instance. And it's kind of the same idea. All right, so let's go ahead and start here. Classification for the iris data set. And really the focus is just going to be on creating this new architecture. So let's open up Colab. Okay, new notebook. We're still using a CPU. I probably won't start using a GPU until we use the third data set, which is MNIST, which will have images, so it'll be much larger, essentially. Let's close that. I will need the data set. Okay, there it is. Let's mount the drive. Okay, so let's click on drive, my drive, and let's find the file, which is iris CSV. Here it is. Copy the path. Okay, so we have our file. Essentially the same thing. I will just quickly load up the different libraries. So we need this one that we described on Monday. Get rid of that. Okay, so we add that library for Torch. We're going to need the tensor dataset and tensor data loader. So remember, those are very useful. And we just have to remember, this is probably an exam type question, right? So I'll give you some data and I'll say, create the list of tuples that you could then easily load into tensor dataset and data loader. Make sense? So just a hint there as far as the exam. All right, so that's the library. We have the metrics, of course. Okay. We don't need Onyx right now, so I won't be using Onyx yet. I'm going to keep things simple. We'll add our variables, same variables, batch size, learning rate, and epochs. Okay, then we need to load the data. Okay. So let's copy the path. All right, and we've got our data loaded as a pandas data frame for iris. Okay. Then we want to do the mapping so that we can exchange the strings into integers. So that's going to be via pandas. So you can see lots of ways of doing, there's lots of approaches to solving problems in machine learning. So we've done this with the label encoder, now we're doing it with the pandas framework. Then we have here, again, you can see for confirmation, we've changed the labels from strings to integers. Okay, I'll skip this part of the correlation matrix. We've already done this in the previous class. But we do need this part, right, to convert the pandas data frame into a NumPy array. Let's add a few more cells. Okay. So then, it's NumPy. Now we need to remember slice X and Y from our data. Okay, so that's done. And then we've already viewed these values, so we can skip that. We do need to, I do recommend you change the data type to integer. Okay. You just want to help the algorithms as much as possible. So if you know that something is a discrete set of integers, set it as that. We already know it's balanced, so we can skip this part. This will be more useful when we look at the wine quality data set, because that's going to be, that's intentionally a noisy data set. So this one's pretty easy, right? Everything is going to work out. That one, on the other hand, will be more challenging. All right, we grab the random seed. Okay, so now remember that helps you so that every time that you run the Jupyter, actually I need to say something about that. The data will be different. So for the competition, you need to give me, and I'll write this on the homework, but you need to give me this, the average out of 10 runs, the average score out of 10 runs. Do you see what I'm saying by that? So you will report, you know, I trained a model, then when I run it on the test set, I'm able to get, you know, 87% F1 measure. Do you see that? But you can't just give me that score out of one run. You have to essentially just, you know, you're going to be using this parameter to set a random seed, okay? So that every time that you run the Jupyter, it's a different, you know, sometimes, you know, you have samples. Some samples sometimes will be used for training. Other times, those samples will be used for testing. So you just want to get that randomization. And then I need to see the 10 scores. So these are my 10 runs, and these are my 10 scores. So then we can look at that and take the average of that. Because what can happen a lot of the time with these machine learning models is you get, one time you get 87. But you run it 3 more times, and it's 82 always. Do you see what I'm saying? So it changes. So essentially what you want is like a tendency. So if you run it 10 times, you'll have a range between possibly 89 and 81, but it has a tendency to be around 86 or 84. And that's going to be the score that we're going to use to determine the winner of the competition. Does that make sense, guys? That's a really important idea, actually. Otherwise, students start like, you know, they think they've won, or you know, so you get, so this is, so we need to have some rules like that, just to make sure that we choose the correct winner. Okay. All right. So so this is important for the randomization, and of course, you always have X and Y regardless of what data you're using. Even if you had ChatGPT, right, and you were training ChatGPT, you'd still have X and Y. So you will always do this randomization. All right, and the split. Let's confirm that I did the split correctly. Okay, so it looks good. All right. And the data type is int, so I want to change the data type to, well, int64, and I want to change it from float64 to float32. Right, so just reducing the size a little bit. So that's done, and then I'm going to convert now these from NumPy to PyTorch. All right, so I got my tensors here. All right, next step, calculate the means and the standard deviations. Remember, if you want to win the competition, you probably need to use normalizations, lots of them. Remember, there's normalization. You can normalize inputs, outputs, and anything in between, like the layers as well. Okay. All right, so we've got our means or deviations. Now we can create the data loaders. Remember, this is possibly the trickiest part. Usually when you're starting with PyTorch, this is the really hard part. So just learn this really well, okay? Make sure you understand what everything means. Go back, but it's a list of tuples, essentially. Okay, so now I can load the data into train.dl. So I've got my train data loader, batches of 16, my test data loader, which is only one batch of 30. like that. So I think we're ready now, and now we're ready, right? So for the new part, so I already covered this one, the multi-layer perceptron. I think it did well. And don't expect this model, just because we're throwing deep learning at it, don't expect it to immediately be pretty good, right? So it takes a lot of work, sometimes a lot of experimentation with the architecture, a lot of tricks to get the models to be better with deep learning, but that's kind of the alternative that you have, right? Like the opportunity. You can build a multi-layer perceptron, but actually you can scale up if you have enough data to a deeper neural network. And that potentially can give you a better model. All right, so I'm not going to cover this one since I've already covered it, but we'll add it in here. And instead, we're going to focus now on the DLNet. All right, so if we look at the scores for this one, they were pretty good, right? 96 essentially. So the DLNet hopefully will get 96, maybe 97, a little bit more. But anyway, the goal is not necessarily to increase the score here, but just to understand how to create a different architecture. So in the previous example, let's kind of start here, right? Let's start with the multi-layer perceptron, MLP. I built an architecture for the iris dataset that is an MLP. So let's go to the whiteboard. Where's the whiteboard? Okay. Okay, so the MLP, multi-layer perceptron, which you've used several times this semester, MLP, essentially we just can define it for our purposes as something that just has one hidden layer. So we've got one input layer. Obviously this is set in stone because this depends on your X data. So in your X data you have 4 features, right? Petal length, petal width, sepal length, sepal width. And then we also know that this is kind of set in stone because for a classification problem, this is determined by the number of classes. So we have 3 neurons, right? 3 classes, Setosa, Virginica, and versicolor. You know, the iris flowers, right? There's one case when it's a binary case, when it's just like true or false or something like that, cat or dog. In that situation, we can have either 2 neurons or just 1, because you have to think this could be represented as 1, 0, or 0, 1, but this could also be 0, 2, 1, right? So the 1 there can go from lower to the maximum. And so we have 2 types of representations that we can use for the binary case. But in this case, we have 3 classes, so this does not apply, okay? So you might see me do that later. All right, so let's focus then here. So for the multi-layer perceptron, essentially we just have 1 layer, and we set that they go from 4 to 3 and 3 to 3. So that means that this has 3 neurons. Do you guys see this? So this is an output, and this is 1 hidden layer. 1 hidden layer, okay? Make sense? All right. So now we're going to build, you should be excited, right? So back on up until like 2015, most people could not build deep neural networks, right? Just 10 years ago. Only like researchers and very specific companies could build deep neural networks. Now everyone can, right? So you have this power. All right, so we have here a deep neural net. This term was coined by Geoffrey Hinton. So I've mentioned him briefly already, right? So he perfected the method of training these models called stochastic gradient descent, the godfather of AI, and essentially he coined the term. So essentially all it means is now we have, we still have an X with 4 neurons. That's still the input. And we still have, notice I'm going to shift this output here to 3, but I now have more than one hidden layer. Do you see that? So essentially I have this one, but this one, instead of going directly and connecting to this object, which is the same, right? So this output, it's the same concept as a hidden layer. It just has a different meaning perhaps, and it's at the end, but it's no different. So that's why we can just extend this concept. So for instance, I can make this be 1, 2, 3, 4, 5. That's my choice. And that means I have 5 neurons. And then, guess what? I'm going to add another hidden layer, H2, and this one only has 4. Do you see that? So that is essentially deep learning. Deep learning is just adding one more of these. And remember, what is one of these segments? Mathematically is quite simply a X matrix multiplication W, right? What is W? The connections, the weight values, right? And then it just produces the next thing, where the next thing here is a hidden layer. If I'm looking at this one, right, then I have another set of weights, right? We can write it over here. So that's going to be what? What's the input to this segment? Not X, because it can't go back that far. Instead, it uses the transformed X, which is H1. So then it becomes, instead of X, right? Instead of X, becomes H1, matrix multiplication, W. Another W, right? Not the same W, because every one of these is different. And what does that produce? H2. Do you guys see that? Each one of these, which is, this matrix multiplication, I'm skipping the bias, but that's included. And remember, we represent these by using this construct called nn.linear, all right, that holds this information. And all we have to do is essentially specify the values that go here, which is usually this 5 and this 4 if this is the segment that we're looking at. Okay, that's essentially it. So we're building here a deep neural network. Could I have 3 layers? Sure, I can have 20. You see that? It's going to be a lot of coding to have 20 with this approach, but I could have another one, and it's 3 for whatever reason. You could make this 30 if you want, right? It's your choice. You're the architect. However, keep in mind, as you add more neurons, it's going to take longer to train because it has to figure out every single one of these connections, every single one of these values. So remember, they're fully connected. That means one neuron is connected to all the other following neurons, and this like that. And then this neuron is connected to all the following neurons. And this one is connected to all the following neurons. And really what we have to figure out is what the values are. Now, if the value becomes 0, sure, the connection is there, but it's got a strength of 0. And then we connect, this like that and that like that, and those have values, and then until we get to the very end. Does that make sense? So that's deep learning, essentially just adding more NN linears in this sequence, okay? So that's what we're going to do now. We're going to build a new architecture with the same approach. So let's share the screen. Okay, we're going to use this DLNet. So notice in this one I have a deep learning with 2 hidden layers. Okay, so in your homework assignment, I will give you MNIST. You can even start working on it right now. I'll give you MNIST for that one. Is black and white black and white images, and what you will do is you will create 2 architectures. One based on this approach, and then one based on something called CNN. All right, so that'll be the homework. I'll give you that next week, though, because you have an exam next week, so no homework this week. Yes, sir?
The homework and competition?
No, there's one homework and then the competition with 2 phases. That's all that's left in the semester. Yeah, but they're related, actually. They will be related. Okay? So one, you use MNIST, which is pretty easy. And then one is going to be a little bit harder because it's a term project. It's still going to be color images, but just a bit more challenging. All right, so let's continue then. Let's focus on DLNet, okay? So this is going to be our new architecture. And it's a good practice to have like a comment of the architecture here. So let's do this. All right, so let's think about it again. So how do we define a new architecture? So before we had class MLPnet, right? One input, one hidden layer, one output. Now I'm going to define a neural net with 2 hidden layers. This is definitely deep learning, okay? So remember, I'm going to remove these sections just to simplify it a little bit for now. So let me remove these and we can add them back. So remember, these are the elements when creating a class for a neural network architecture. So you have the name class, right, for the definition. Then you have the name that you want to give it. So in this case, I'm calling it DLNet. Sometimes you can call it something like DL2HNet. That means 2 hidden layers. Remember that we're using class inheritance. So we inherit the NN module from PyTorch. And then from there, we're going to define all the things. Remember, it's got 2 functions, the constructor init, and then it's got the forward function, right? So just like before, we had init and forward. Okay, and in it, we specify the variables, define things, and then in forward, we connect the whole architecture from input all the way to output, all right? So that's essentially the idea. Same approach, we already calculated x means and x deviation, so we'll pass that to the class when we instantiate it. Okay, so we initialize the inherited class and everything. And then remember, we can use self dot to create internal variables within the class. So we're going to assign x means and x deviations to these internal variables. Okay? I'll focus on the init part first, and then we will move to the forward function, right, just to see how everything goes together. Okay? So let's start here. So in Monday's lecture, I used 2 NN.linears, right? So I had had self-linear 1, self-linear 2. So I was using 2 NN.linears. Here, because I have 2 hidden layers, I will have to use more, essentially. All right, and so I'm just going to label them and define the parameters. So let's go ahead and create the first one. So I'm going to call it self.linear1, and I'm going to define it as an NN linear from 4 to 15. Why 4 to 15? 4 we know because that's the size of the data of x, right? It's got 4 features. This 15 is my choice. I want the first hidden layer to have 15 neurons. Okay, so I'm giving it a lot of power, right, essentially, to process the data. Remember that when you go from one layer to the next, you want to use activation functions. Okay, so notice here I'm not using the sigmoid anymore, but I'm using the much more powerful ReLU function. So ReLU function has been found to be pretty good for defining deep neural networks. So notice here I have activation 1, NN ReLU. This is called a rectified linear unit. They also call it the hockey stick activation, and the reason for that is that it only passes positive values. So here we can see I'm defining, let's move to a new, I'm defining this part of the neural network. Okay, so I've said it's got 4, 1, 2, 3, 4. That doesn't change because that's the x, that's the input, right? NN.linear for this one has 4, 15. So what that means is that this next layer here, H1, has 15 neurons. So 1, 2, 3, 4, ... 15. Does this make sense, guys? That's essentially what I'm doing with the definition of the architecture. And then the activation will apply here. Once I've done the initial calculation, all these values will be passed through that ReLU. NN.ReLU. It's called, as I said, the hockey stick. So what that means is essentially that it looks like this. See it looks like a hockey stick. Do you see that? So what does that mean? So if the values are negative, it always just converts them to 0. Okay, so anything negative, because this is 0 to actually to infinity, to plus infinity. Right? So if it's negative, it becomes 0. But if it's positive, then it just passes the value. So for instance, if I have a ReLU, nn.relu, and it takes in the value -3, then it's going to produce 0. But if I have nn.relu, and the value is, let's say, 17, then it just lets it through, 17. All right? So that's what the ReLU function does. And this apparently is a really great activation function for deep neural networks. Any questions on that, guys? Yeah. All right, so the rectified linear unit, very powerful. It's essentially, if we want to define this function, it's pretty simple, actually. So we just do, I think it's something like max of, oh yeah, sorry. So the function is defined as z, where this is going to be the max of either 0 or z. Do you see that? So if it's negative, it picks 0, or the c value. All right, so now, so we take our data, right, it's fully connected here. It goes from 4 to 15, and then we run that vector of 15 through the ReLU function. Essentially, anything negative is turned into a 0. Everything positive is allowed through. All right? So that's the first one. So now let's go back to our code. All right, so I've done this segment. Now I'm going to do the next, as you can see here. Now I can copy, since I understand, I can copy both of them at the same time. This defines the next segment. So you can see here, I'm calling these now linear 2 and activation 2. This next one, remember my architecture is 4 to 15, so I have to start at that layer. So this value, 15, needs to match this value here, okay? But now I'm defining that the next layer is going to be 9. Do you see that? So that means I'm going to have another hidden layer, and that one has 9 neurons. And then once those are calculated, you're going to run those values through the ReLU activation again, so that it'll have its own ReLU activation. All right, and then we have this last layer. We have this last layer here. And this last layer, we call it linear 3. This is the output layer. Notice, because this ended at 9, then this one has to start at 9, and it'll go all the way to 3. Where 3 are the, basically the output layer, where we have 3 neurons for the 3 classes. Remember, I explained this on Monday already. The activation that we want to use here instead of ReLU for a classification problem in the last layer, you can run something called a softmax. And essentially what it does is that it makes sure that all the values in that vector add up to 1. Okay? And then this dropout we can ignore for now, but it's helpful to have this every now and then. All right, and that's it. That's the architecture that we have defined. So let's now draw it out on the whiteboard. So remind me if I forget. So it goes from 4 to 15, then to 9, then to 3, right? So 4 to 15 to 9 to 3. So what does that neural network look like? Okay, so now we can go over it. So it's got 1, 2, 3, 4. This is, remember, the input layer, 4. What was the next one? Hidden 1. And it had how many? 15, right? So 15 neurons, dot, 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 15. Then the next layer had, we call it H2, and it had 9, right? 9 layers. So 1, 2, 3, 4, 5, dot, 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 9. And then the last layer had 3. Do you guys remember that? So it's 3. And we call it output. So that's it. That's, with that code, you've created this neural network. Does this make sense, guys? And remember that NN linear, essentially, it's doing all the heavy lifting for you, and it's just a matrix multiplication. Although you don't see it, these are inside NN linear, these weight matrices, right? So you're multiplying, remember, this is X. You're doing, so now if I want to write this neural network, right, from beginning to end, like in functions, how do I do it? Well, it's going to be X matrix multiplication W1 plus B1, and that's equal to what? H1. Do you guys agree? And then the next step of the network is now from H1, right? So I replace X with H1, matrix multiplication W2 plus B2 is equal to what? H2. Do you guys see that? And then now the next step is going to be what? Instead of H1, H2, matrix multiplication, W3 plus B3, and this is equal to Y pred, or output in this case. Does this make sense, guys? So essentially I've shown you 3 ways to represent the neural network here. One in diagram form, one in equations and functions, and of course one in code. So on the exam, you can expect 2 out of the 10 problems at least to be similar to this one. All right. So I may give you the code and I ask you to create the diagram. I could give you the diagram, ask you for the code. I could give you the functions, ask for either one. Do you see that? So I'll do something like this. So make sure you understand it. So are there any questions about this? Yes, sir. Ben. Yeah. You can use software on your computer, or you can, some students take a sheet of paper, draw it, take a picture, put the picture in the exam. That's fine too. Does that work? Yeah. Yeah, you need, but you can draw also on Word, like circles, and however you want to do it. But it's important that we understand, right, that this is when people say a neural network, right, the thing that's most intuitive in terms of being a neural network is this one. But obviously we can't just create a diagram in a program. We have to code it. But you have to know also the underlying thing is that you have these functions. Remember that this translates into, we're not using the actual matrix multiplication. We are just defining NN linear. So essentially we're just doing NN linear, and it's going to be 4, 15, and then it takes X as input. Do you see that? So that's the way that you can think about it. Then you have H2, which is NN.linear, and this one is 15 to 9, but its input is what? H1, right? This one over here. And then the last one, Y, is going to be NN.linear, 9 to 3, and that's H2. And notice that I did skip the activation function, so really the activation functions would be there. Got it? Any questions? All right, so it seems like it's making sense. So let's go ahead and finish it then. Let's put together the architecture. So we've defined everything. Let's need to share. Okay, so we've defined these elements. Now, remember, the network is not connected yet, right? So we have to connect it in the correct flow. So the first step is the forward function, which is the model. So when you have model, you kind of just say model, but it's essentially you're saying model dot forward. So either one of those approaches would work, but this just makes the code more readable. So you just give the input to the model x, and then remember I talked about this on Monday already. So we standardized the data, right? We already calculated the means and the standard deviations. So this is a really good practice in machine learning that makes a huge difference. All right, so we've done that part, and then now we can just start using the different sections, right? So notice that we don't use NN linear, instead we reference linear 3 or linear 2 or linear 1. So here, obviously, I'm going to go for the first one, linear 1, so self.linear1, so it takes x as input, and it'll process it and assign it to x. So it goes from 4 to 15. Then that x explicitly goes through the activation function, which is a ReLU, the hockey stick. That gives you an x here. Okay, then after that, I do the second section. Okay, and this one takes x. Oh, I have a dropout in here. Okay, so the dropout is a technique to force the model to sometimes ignore some of the network connections. So here, for instance, you're saying I have a dropout of 0.25. So I'm actually telling the model, okay, do the training, but sometimes assign a 0 when you're training to some of these connections. And the idea is to kind of help it to generalize, and it's a strategy that can work really well. All right, so I've added the dropout. Notice now I'm going to add the second section, which is going to be this one, the linear 2s. So I have x comes into linear 2 to produce x, then that x goes into activation 2 to produce x, and again it goes into the dropout to produce x, essentially. All right? Then I do the last step. The last step does not need a dropout, but it does need, this is the part where I go from 9 to 3, right? Take my data from 9 to 3, and then I run it through the activation function 3, which is the softmax. And essentially that vector, remember, which had values like 0.6, 0.8, 0.5, if you take those three, they are over 1, greater than 1. So you run them through softmax, and softmax will adjust those values so that they add up to 1. And it becomes a proper probability distribution. I already explained that already in Monday's class, so you can look back to see why we want to do that. All right, and that's it. That's how you do a second architecture, right? So pretty straightforward. Oh, and I forgot to return the YPRED. So I really like this method because it's like you guys get a template. It's essentially how it is. You guys now have a template, and it's always going to be like this. A class, there's going to be an init and a forward, and if you learn this structure, you'll be able to solve many problems with machine learning. All you have to do is what? Get your data. Figure out the shapes, convert it into X and Y, right? And then what? Split it. Put it in those list of tuples so that they fit into the data loaders. Build the architecture. You're done. And now you can solve any problem, and any real problem, because this will work on the GPU. You see that? So I'll try to switch over to the GPU in a second, and you'll see that it'll run there. And here we don't need a GPU, but if you had that's why I'm giving you one homework with MNIST, so it's a bit more challenging, and you can see that it takes a while to train. All right, so the architecture is done, which is really great, and you have now built your first, maybe it's not your first, but it could be your first deep neural network. Not for you, right? So you build a lot of deep neural networks, but there it is, your first deep neural network. All right, everything else we've already explained in Monday's class, so we don't have to go over them. So now it's going to be the same train loop. same train function. You know, we're going to treat it, the model doesn't care, right? If this is a MLP or it's a deep neural network with 17 layers or if it's a CNN, it's just a model, right? So inside it's got its architecture. But at the end of the day, an input goes in and an output comes out. That's it. That's the trick. All right, so here, remember everything that I've discussed so far is for classification. So I'm going to show you later classification and regression as a contrast. All right, so let's go ahead. So I've explained this already in the Monday class, so let's go ahead and run it. All right, that's the training function. And now we can go ahead and train the model. You see that there? Instead of notice that instead of using the MLP architecture, I'm going to now instantiate the DLNet. You see that? The DLNet class that I just defined. Optim is defined here. Notice that I still pass model. I link it to optimizer here so that I'm telling it the thing that you need to train is the weights and biases of this class that I just created, right? And then the learning rate is specified. This part, cross entropy, that has to be its own separate class. For now, just think of it as I take the predicted and the real, and somehow in there I'm going to compare them. Okay, and it's going to give you this idea of loss. You can think of it a little bit like the Euclidean distance from K and N, if that helps you. So if you remember in K and N, we had the predicted and the and we one value, the current value, and all the samples. We take the distance, and that would give us a value. You guys remember that, of course. And so think of cross entropy a little bit like that, but it's not. So I'll definitely describe this. Now, what I'm going to say right now is key. Make a note of this. This is probably a question on the exam. When you're dealing with classification problems, you will use cross entropy. Okay. When you're dealing with regression problems, you will use another method called MSE. So make a note of that, because that's probably going to be a question. I'll say something like, which loss function do you use for classification and which loss function do you use for regression? Okay, just like in the past I've asked a question, what's the difference between classification and regression? So there's a difference, but now we need to actually, this is a place where they change a little bit. Okay, so we have these different methods. So just make a note of that. All right, so this is still classification, so I'm using cross entropy. I'm going to go ahead and run, and as you can see now, it is training. In fact, let me stop it, and I'm going to switch over to the GPU, change runtime type, so GPU. So now I'm using a GPU, essentially. And so the only thing is that it like reset the environment. So I just have to run everything again. But if you notice, it's the same code, right? I don't have to change a single thing of the code. I just have to select the device that I want to use. Later on, as it gets a little bit more complex, we have to specify, okay, CPU, GPU, etc. But we don't have to change too many things. See there. And if you notice, it's running a little bit faster, right? Just a little bit. Do you see that? This will make a difference when you start using really large data sets. I mean, you're talking about 4 hours versus 1 hour. I think it's a factor of 10, actually, is what they usually say. But you can see this is running fast. And we are, in fact, running this on the GPU. Got it, guys? Does this make sense? So that's the idea, right? So you've learned this framework. This framework now allows you to use GPUs efficiently and train your models faster, train more data, and so on. Train bigger neural networks. So this, from here, this was the first time that we use a GPU. We don't really need a GPU here, but the data will get bigger. Once we introduce CNNs, the architectures are more complex. Once you introduce transfer learning, it's going to be even bigger models. So at some point, you're actually going to hit a limit because things are just too big. Okay, so that's kind of where we're going. Definitely phase 2 of the term project is meant to be that. It uses transfer learning. You have to use a GPU, and it's just going to be more challenging. All right, it's done. So it finished. Okay, and now all we have to do is look at the evaluation part, right? And in that, we've been doing that all semester, so that should be pretty familiar to you. We use the same function that we've used in the past. We're using sklearn, in fact, to print precision, recall, fmeasure, and so on. And notice here, we're going to do that, right? So with torch no grad, that just means that we're not in training mode anymore. Also, there are functions where you can tell the model to be in training versus testing, something like that. So there's various ways of doing that. But here I'm just saying with torch no grad usually means grad is the gradient. So it's referring to the calculation of the weights. So no update happens here. Notice that we created testDL. So here I'm just grabbing x real and y real from the test set. Okay, from evaluating. If you remember, the batch size was 30 here. So essentially we just do one run. We give all 30 to the model. Here, all 30 samples. It gives me my y-pred. But you should be aware that y-pred is a tensor of size 30, 3. Okay? Y30, well, it's 30 test samples. Y3, because the last layer of your neural network, linear 3, right, is 3. Okay? That's really important. And so obviously what we have is, for every sample, we have the probability distribution. Okay? So this max function here, this max is essentially picking what? The index of the highest value. And then once I have that, both preds and the real values are given to my performance metrics function, and that gives me the final result. And there it is, 96. So we got the exact same thing using the DL net. Again, here in Iris, a multi-layer perceptron was really good, so DLNet is not necessary, right? But in other situations, adding more architecture might give you better performance. Do you guys see that? So that's essentially the idea. That's it. So now you've done 2 architectures with the same PyTorch approach. Are there any questions, guys, before we move on to the next example? All right, perfect. So it's making sense, right? So now we're going to move on to a new data set. This is a more complex data set, right? It's not going to be like Iris, right? Which, you can get really good scores with Iris. We're going to switch to another one we've used in the past called a wine quality data set. But that one, if you remember, was more geared towards regression. It's not really a classification thing. So although I think you've seen it, you did do it in classification. I think you just weren't able to train the models that well, right? I believe. Okay, so anyway, we're going to use that one. I'm going to essentially do the same thing. I'm going to load the data and create the architecture. So let's go ahead and close this one. So I'm going to switch over now to classification DL, deep learning algorithm, PyTorch wine. All right. So I'm going to use, do the code again, kind of the same pipeline. We're going to build a different architecture, and we're going to look at the performance of it. Okay. So let's go ahead and do that. So I'm going to open up a new Colab. So new notebook. I'm going to switch back to the CPU if I can, as I don't really, because don't consume your GPU resources, right? Don't use it unless you have to. All right, so now let's do same thing. So I set this before, right? The first class is hard, but after that, there's a lot of repetition, right? So it's the same libraries, as you can see. Because really, what are we doing? We're just taking another data set. We're going to process it in the format that PyTorch likes, and then we're going to build neural networks for it. Right? So the same libraries, so we can add those, no problem. Let's get the next set of libraries. Tensor dataset, data loader, as you can see. Okay, that loaded. Now we do this one. Loaded correctly. The metrics, again, this is still going to be a classification problem. The focus of this example with the wine quality data set is that I'm going to use the same data set for both the classification problem and the regression problem. Okay, so the idea is that you see the differences. I think like 85% of the code is the same. It's just a few small differences here and there, or a few tweaks that you have to implement. Okay, so I add the metrics. Okay, I'm not sure if I'm using Onyx in this one, but I might as well start adding it. So remember, one key thing is you don't just want to train a model, right? You want to use it. So you're going to be deploying your models to GitHub pages, just like you did for the Perceptron homework, right? Where you're deploying on GitHub pages, you'll do the same. Still using HTML, CSS, JavaScript, but now you're going to load this model there. So we need something called Onyx to create these files. That's like the state of the art in how to do that. So let's go ahead and install these. So I need Onyx runtime. So I think I have. Yeah, so let's just try adding these. Okay, so I think Onyx runtime it was complaining about. So let's give it a minute. All right, so that worked. And then, all right, and then Onyx ML tools, so that's the other one. So let's run that one. So for TensorFlow, for instance, TensorFlow developed its own tool. And so you can, similar to Onyx, and then you can deploy that model. As I said, we're using PyTorch, so PyTorch has this different methodology called Onyx. Onyx is a more general approach, so it works for more libraries than just PyTorch. All right, so let's try it now. All right, great, perfect. So we got a green check, so that means that Onyx tools are now available, and we'll be able to start deploying our PyTorch models. Essentially, it just creates a little file, and then you can take that file and move it around as you need to. All right, so now let's go to yeah, so we added these libraries. Now if you notice, again, the parameters, same thing as before, right? So it's a different data set, but you still need to know the batch size. Notice here I'm changing the batch size to 32. The learning rate is 0.001. I'm only going to do 1,000 epochs. These are parameters that you can change depending on your problem. The epsilon is usually so I don't have division by 0 errors, things like that. Okay, so that's done. Got my parameters. Now I need the wine quality data set. So I just need to know the path in Colab. So this is the same file I had used before. Okay, my drive. All right, so we need to find, oh, here it is. So let's copy the path. All right, so we're going to use the same approach, create a pandas data frame. Let's print the pandas data frame just to confirm that everything looks good. Okay, looks good, right? So you've got, I think this had 11 features, and you did this for a WECA homework possibly, or sklearn. You got your quality values here. Now this is a harder data set to deal with, right? So we're going to have to do maybe some cleanup or at least some analysis. We know for a fact that we have 5,000 rows, so 5,000 samples. We have 12 columns. The first 11 are the X features, and the last one is the Y. So if it's a regression problem, then it's just these numbers. These are ratings from 0 to 10. But also because we just have these values, 0, 1, 3, 7, we can treat this as a classification problem. Do you guys see that? The only problem is that there may be missing ratings. So for instance, no one ever assigned a 3. So therefore in here we don't have 3s. We might have a 2, a 4, a 5, but no examples of 3. So PyTorch does not like that. All right, so we have to do a little bit of tweaking of the data. We'll do another mapping just so that we don't have any gaps in the sequence of the discrete values. You'll see what I mean by that. But that's only for the classification problem. For the regression problem, that should be fine. But before we do that, we should start looking at, do some analytics, right? Some data science of the data. We want to visualize our data. I always like to do this first. The first thing I do is just look at my data. I print out the variables, look at the distributions, things like that, just to get a sense of what everything is. So we can do the correlation matrix again. This just, if anything, I run this because the correlation matrix, if it looks like this, then the data is good. Sometimes you'll see like zeros, or some area here is like white or something like that, and it tells you that there's something wrong, some kind of a problem in the data. All right, but here you can see it looks good, healthy, if you want to call it that, and so it should be fine. All right, and of course there's meaning. You can see which variables are correlated positively, negatively, and so on. So that can give you insight as you start analyzing your problem in more detail. All right, so now that this is done, let's go ahead and just convert my pandas data frame into NumPy. Notice I'm using the exact same pipeline. I like consistency. This is how, so all the code examples are pretty consistent, right? They follow as much as I can, make them consistent, that they will be. All right, so now I've created this as a NumPy matrix. So let me go ahead and print it out, and there we are. So I have my data. All right, now I want to start maybe creating a histogram. I want to see if it's a balanced data set, things like that. So of course, I'm going to need to split the data first. I'm going to split it into my, X and Y, right? If you remember, I said this at the very beginning of the semester, right? When we look at the word problems, machine learning word problems, right? By the way, you could get one of those on the exam, right? Again, right? So on exam 2, there could be one more of these. Remember there, the key thing is I want to see the shapes of X and Y. You need to put those numbers in there. So here I'm going to take the first, notice, I'm going to take the first 11, I'm going to slice them out, and then just take the last column and assign it to Y, right? So I have my X and Y now defined. Okay, great. Probably a good idea to kind of print the values. I'm going to convert these into integer since they're float. Because they're, I'm treating them as labels here. And now I can start looking at the set. So you can see how this is useful now, right? I want to look at Y, and I want to find all the unique values in there. Okay. See, this is something that you need to pay attention to when you're dealing with a problem. So when you guys do the MNIST dataset will have, there's 10, it's called a dataset of handwritten digits. So it's going to be digits 0, 1, all the way through 9, right? So 1, 2, 3, all the way to 9. So there's in total 10 digits. So that means there's going to be 10 classes, right? So when you do something like this with MNIST, you can expect that it would go from 0 to 9. There's not, you won't have any missing digits. However, in this example, or missing classes, I should say, in this example of the ratings, what do you notice? We have 3, 4, 5, 6, 7, 8, 9 represented, but we have no values for 0, 1, and 2. So essentially what that means is that when they were rating the wine, no one gave it a 0 or a 1 or even a 2. They always started at 3. But this is a problem for our modeling here because PyTorch does not like, in a classification problem, PyTorch does not like missing classes. You cannot have this. Okay? Do you see that, guys? So it has to start at 0. This is key, and this is something that a lot of people miss, and you can spend hours trying to figure out what the problem is. Okay, so just be aware of this. PyTorch does not like this. So you have to fix this, and the best way to fix it is just to do a mapping, like we did before with strings to numbers. So now you're just mapping from number to number. So essentially, we're going to say that 3 is what? A 0. 4 is a 1. 5 is a 2, and that way we're not going to have any missing values in the sequence of classes. Got it? Does this make sense? So let's see how that would work. Okay, so these are the values. We know we have 7. We can also, before we do that, we can also plot the histogram, which is also really important. So we want to see, first of all, we want to know if for these classes that we have, that we're going to map in a second, is the data set balanced or imbalanced? So what do you guys think? Do you think it'll be balanced or imbalanced? Well, let's see, right? So let's take a look. All right, so if I gave this to you on the exam and I asked you, is this data set, this classification data set, is it balanced or is it imbalanced? What would you say? It's what? Balanced or imbalanced? You say it's balanced. Why? Oh, so because of the bell shape, right? Okay, but see, that's a normal distribution. But if you look, for instance, let's go back to Iris, right? So this is an important one. So in Iris, I also did the histogram. See that? So balance here means that we have 3 classes, but for every class we have about the same number of samples. So it doesn't have to be exact, but it has to be close. So for instance, here we have 50 for class 0, 50 for class 1, 50 for class 2. Do you guys see that? This is what I mean by balance or imbalance. We know that the machine, this is important actually, really important, because by looking at this, I know that the results are going to be probably pretty good. Right? It's an easy problem for machine learning. But this one, on the other hand, I have this class, this class, this class. So actually I have a dominant class, right, which is 6. This one has a lot of samples, over 2,000 in fact. But what about classes 3 and 9? They only have maybe 10 or 20 examples or samples. Do you see that? So this is actually a highly imbalanced data set. In fact, if I was doing this, what I would do is I would essentially just create 3 classes. I would combine these 3 into one class, and then these 3 into another class, and I would probably leave this one as a separate thing. Do you guys see that? To make it more balanced. Do you understand now? So what you were thinking about, it does actually look like a normal distribution, right? Which means it's got a mean and a standard deviation. But the question we want to answer here is whether we have enough samples for each class to be represented, or do we have one class that will dominate. So what happens in machine learning is machine learning will learn this class really well. So class 6 is going to dominate essentially because it's got a lot of examples of it. Do you guys see that now? So this is important. Whenever you're doing, let's say somebody hires you to do some work or something in machine learning, you should, for classification, always look at this. This tells you a lot already. You're like, oh, you should be happy if you see this. Or if, maybe this is 40, this is 60, this is 30. That's still balanced, right? But this one is just highly imbalanced. It's a pretty difficult thing. So that's why I actually I selected this one. So we're going to use this one to play with deep learning, just so that you can see that it's still challenging. Okay? So let's go ahead then and continue. So I've created the graph. This is a highly imbalanced data set, the histogram. But as I was saying, PyTorch let's take a look here. Oh, sorry, I'm looking at the wrong thing. Let's go back to this one. Okay, so we were here. All right, and I've done the histogram, and you guys understand that now. This is where I do the mapping, so we're going to do it later. So let's take a look at, let's just print the shapes to confirm that everything is good. Okay, so I have 11 and 1, so that's good. Now, I'm going to split the data into train and test, right? So the same thing that we've done before many times, same function. I'm going to use a random seed, and then I'm going to split X and Y into my X train, Y train for training, and my X test, Y test for testing. Okay, so just give me a second. Okay, so let's do the split. Now let's, we can print the shapes just to confirm. I always, it's a sanity check, just always check the shapes. All right. Change the data type, so we can do that fairly quickly now. So just reduce it to float 32. Okay. And now we're going to create the torch tensors. Okay, that's done. So everything, we have the data in as torch tensors. We still want to do the means and the deviations just like before, and we're still going to use the same type of architecture. We want to either normalize or standardize our data. Okay, so that's good. Okay, so now here's the mapping that I was saying before we create the data loader. As I said, PyTorch does not like missing classes, right? So it does not like, it wants to have a sequence of classes from 0 to 3. So we have to create a mapping. So notice I'm doing a label map here and a reverse label map, just so that it's quick to, we can quickly retrieve this. So I have label map, and notice everything that's a 3 becomes a 0, everything that's a 4 becomes a 1, all the way to everything that's a 9 becomes a 6. So essentially I have like 7 classes in this problem, right? That's important, what I just said to you guys, 7 classes. You're going to use that information to define the architecture of your neural network, right? So that's a value, remember, 7. Right, and then the reverse map is once you have the model predicting, it's going to predict a 0, you need to convert that back into a 3 because it's really, the rating is 3. All right, so we create the label map. And now we can just go ahead and create our list of tuples. All right, so I'm going to do this for train first and then for test. Notice this part is what I've mentioned before, right? That it can be pretty difficult to go from data to Torch data loader. But if you have this mental model in your head, then it should be pretty easy and straightforward. So what you need to do is, because you'll have to do this for phase 1 and phase 2, right? So remember, we're creating a list of tuples. So this is a list comprehension. We iterate for I in range of X trained data. So we have about 3,000 samples, I believe, or 4,000, something like that. Right? So we grab by index I, we're going to fill in this tuple with this value and then this value. The first value should be pretty easy. It's just X trained TR I. Right? So vectors of what? Here, vectors of 11. Remember, I already explained this part in the lecture on Monday, but essentially you're just grabbing every vector of 11 and you're putting it in the first part of the tuple. That's highlighted in blue. Then in the second part of the tuple, I put in the label. Do you see that? That's going to be the number, not a vector-wise label, but just like the integer. Okay, so the label could be a 6, right? But remember that we need to encode it, so really 6 should become 3. So that's why when you grab this, first you're going to go into Y-train TR and you grab that index position. Let's say you grab the 6, right? We do item because it's still a vector, so we want to take it out of that vector and just have the value itself. So now here I have the number 6, right? But we still need to map it with the label map, so 6 goes in label map, and label map will return 3, and that's it. Got it, guys? You could have done this outside of the loop also, but this is just less code. Any questions on what I did here? All right, sounds like you understand. So yeah, so I'm creating my list of tuples here for the train data, vectors of 11 here, and then the labels, but just mapped through the label map. So I do that for train, then I do the same for the test data. I'm going to create a list of tuples for that, of the vectors and the y's, and that's it. Once I have this, I can just load it onto the data loader, right? So that's what's so great about it. You can print it if you'd like. Here I'm just now adding it to, creating a PyTorch object called a data loader. You can see from torch utils data loader, I'm going to grab Y-train list. I'm going to specify the batch size, which I think is 32 now, and I'm going to shuffle, right? So every epoch, we shuffle the data, all the tuples, and then we start grabbing batches. So you can see it's exactly what we did on Monday with the iris data set, very repetitive, and that's good. you want this template. You want it to be predictable, right? So you want to know that you can always just follow the same number of steps. So now we do the same for the test set. Now this one has, I believe, 1,000 test samples. I can't remember exactly, but we can check. So let me print this value. Oh, 980, right? So there's 980 test samples. But because this is testing just for the evaluation, we don't need to be efficient here. So usually what I do is I just create one batch of size 980. That's it. And so that one I will only iterate once through the data loader, grab all the test data, and that way I can just give it to the model to do a prediction. So notice this is important. I pay a lot of attention to this on the homework, right? Because I explain it a lot in class, and so don't get this wrong. All right, and then we have the shuffle here, and that, as I said, is just to tell the model to randomize the tuples every epoch. All right, so test DL has been created, train DL also, and now we're getting ready for the architecture, right? So once again, we're building another neural network in the same we're going to take the same approach as we did before. Notice here I have an architecture, I have an MLP, and I have a DLNet. Same idea. Do you guys see that? Since you guys probably already understand the MLP, I'm not going to do that one. I leave it for you guys to try at home. All right, and let's just focus on the more complex one, the DLNet. Right, so let's build this one up for the wine quality data set. So again, I'll copy it and do the exact same thing just to illustrate that it's always pretty consistent. See, this is a different data set, different dimensions, different things. But if you simplify this first, you will see it's exactly the same thing. We're defining a class in Python. We give it a name, DLNet. We're doing class inheritance of the NN module, which brings in all the features that allow us to define a neural net, deep neural net. We have two functions, the constructor, or init function, and then we have our forward function, right? In the init, we just define all the variables, all those things, but then we have to put that whole flow together in the forward function. All right, notice this x means the next deviations, right? So it's like already part of it. So whenever we initialize the class, we instantiate it, we provide these parameters, and then they get internally assigned to variables of the class. So it's easier to use them. All right, so I'll focus first on the init function once again, and then we can take a look at the forward function. All right, so let's see. So if you notice here, I'm using ReLU again. I'm going to use linears and softmax. So it's very much the same thing, and I'm just changing some of the values here. These numbers obviously need to change a little. So let's start with the first pair, because remember, every hidden layer should have an activation function, right? Which one am I using here? The ReLU, the hockey stick. I could ask you on the exam, what does ReLU do? So if it's a negative value, it returns a 0. If it's positive value, it just lets it through. Okay, so just remember that. Okay, so notice I'm creating linear 1, the first, the first part of the network from 11 to 15. So what does this mean? Why 11? Can I change that to 14? Why 11? Why not 25?
Because we have 11 features.
Yes, we have 11 features, right, in X, exactly. So that's why you always print the shapes. You know, it seems like a trivial thing that I'm just doing because I'm crazy, but actually, this is the reason here, right? Why are you always printing the shapes? because you want to start looking at this. 11. Okay, you know 11. I have 11 features in X. There you go. I understand that. I have 7 classes also. Do I have 7 classes? 1, 2, 3, 4, 5, 6, 7. Yes. So that's another important value. Okay? But yes, exactly. Good job. So that's 11. All right. So that's why this needs to be 11. But from there, the next layer, the next hidden layer can be something else, right? So you're the architect of the architecture. So you can try different things. So here I'm defining it as 15. So now we can look at the next layer from hidden 1 to hidden 2. There you go. You can see if this one is 15, then this one needs to be 15. Because it's essentially you're going from the input to hidden 1 and then from hidden 1 to hidden 2. So this has to match. Okay? So that's why this is 15, 9, and I'm using another ReLU activation. Then I do the last layer for this one. Keep in mind also on the exam I could ask you to just write this part of the code, but for a deep neural network with 5 hidden layers, right? So you have to then think, okay, what code do I need to add for this to be, for it to have 1 input layer, 1 output layer, and 5 hidden layers in between. So here you can see this third layer goes from 9. So this has to start at 9, and then it goes to 7. Why 7? Can it be 8? No, right? It has to be precisely 7 because we have 7 what? 7 classes, which are the 7 ratings. So in the iris data set, that was 3 because we had setosa, virginica, versicolor. Here it's 7 because we have 7 ratings. All right, that's it. Right? So and then the activation function, activation 3 is softmax. I've said this already to make sure it adds up to 1. The dropout is a technique that just be aware you can use every now and then. And that's the init function, right? So that's defined. Now we put it together. And actually, let's draw this out. So so remind me, it's 11 to 15, 9 to 7. Okay, so let's go to the whiteboard. Because these are the types of questions I can ask on the exam. So for this wine quality, for classification, I'm creating, so I have input 11, so ... 11 neurons. Then the next hidden layer, hidden 1, was 15, correct? So 15, ... Then the next one is 9, ... 9. And what was the last one? 7. ... Here, don't forget, these have to go through activations, and these are both ReLUs. ReLU. And then the last one also goes through an activation, but this is called a softmax. These are very nice little equations, almost standalone. I think actually if you read the notes, it should be in there. Okay, there's a lot of things that I just don't have the time for, but if you go into those notes, there's a little Python example in there where you can see how it does give you something that adds up to 1. Right? So make sure you go through the notes, please. All right, so let's go ahead now and go back to sharing the screen. All right, so we've defined the architecture for this wine quality, all the elements. Now let's put it together. Okay, so we're going to go ahead and put it together. All right, so we do the first part, which is the standardization, as I've mentioned before. every x sample that goes in, it's this equation, minus means divided by deviations, and that just makes the data be within a scale of -5 to 5 for all values. That's actually really helpful. Then that x will go into the first layer, if you will, linear 1 activation 1. All right, so it goes into linear 1, so it goes from what, 11 to 15, right? And then it goes through a ReLU. Then I'm going to do the next one, and there's a dropout. I'm forgetting these dropouts. Let's just add it there. It's still going to work without the dropout, so I encourage you guys to like comment these out and just see the performance. But sometimes when you're training a model, adding this idea of dropping a few connections during training randomly can be helpful. So I introduced this as one of the things that that's available when you start doing your homework and your project. All right, let's do the next layer. You can see here this one, x goes into linear 2, so now it goes from 15 to 9. It goes through the activation ReLU. Remember, it only passes positive values, and then it goes through a dropout. And then finally, it's going to go into the last layer, linear 3. And this one goes from 9 to 7, right? 9 to 7. And then it'll go through this softmax function so that the values add up to 1, and you return ypred. Okay? When a batch comes out of this, it'll be 32, 7, right? That's the output that you get. 32 test samples, each of 7 columns, because that's the probability distribution given the classes. And there you go. You just built your third deep neural network with your second data set. And that's it. Now any problem that you have, as long as you can get the data into that X and Y, you can solve with this approach. That's what I've said many times in the class, right? Instead of always writing the code, no, actually, this is the code. Just get your data into the format of X and Y, and everything else. You have to tweak a few things here and there, but everything else should work. The same exact train loop, right? So this is like the third time we're using it. Exact same idea. From train DL, you grab XB and YB. What's the size of XB? In every iteration, you grab a batch, right? If I asked you on the exam, I just give you this part of the code with some information about the data set. What's the dimension of XB? So it's a matrix, right? What's the dimension? What's the size of the batch? In this case, 32. So it's 32 comma what? It's X. It's what goes into the network first, right? So what was the size of the first input in the network? No. 11. Do you see that? It's 32 comma 11. Exactly. Very good. All right. So now what comes out of the network right, is the YB, right? So, but here, the Y is not it's in a vector form, not a matrix form. So it still contains like 3, 4. So this is going to be 32 comma 1, okay? Because it still has just in that column, it just has the actual label, like a 4. Now, XB, which is a tensor of size 32 comma 11, goes into the model itself, the entire architecture, right? It goes through input 1, hidden 2, output, and output. So what you get out here, ypred, is the output. So now, what's the dimension of ypred? this is another type of question I can ask on the exam, right? So what? Pretty simple. So what are the dimensions of y pred? So it's, if this is a batch of 32 inputs, right? So you're giving it, it's like you're giving it 32 images, and it's supposed to tell you if it's a cat or a dog. Do you see what I'm saying? So you should get 32 predictions. So y pred then is 32 comma what? How many neurons do you have in the last layer of the neural network? The output layer. We saw that a second ago. Seven, right? Why 7? Because there's 7 classes. And then out of those, so your batch y pred, if you have an input of 32 comma 11, you get 32 comma 7. You know, whatever is in here is just transformations, but all that comes out is what comes out of this. So it's 32 comma 7. And from there, we have to select the index of the maximum value. Okay? So we did something like this with K and N. Because this is like a probability distribution. Out of all 7 classes, it's going to say which one has the highest probability, if you will, right? So that's, or likelihood, I should say. So that's the idea. Okay, we're almost done. So yeah, so 32 comma, so make, and also I'll give you this hint. Here, I actually show you how you can look at these values. So if you want to try this out with like different data sets and practice at home, just put an input. I usually, whenever I want to halt a program and just look at whatever is in there, I just do something like that. Does this make sense, guys? Input, and then it'll print the shape of the tensor that you want to confirm. All right, so I'm going to comment these out again, but you have it as a debugging tool or for your own, for your own reference. Anyway, so then we get y pred. What do? Remember, we said like with the Euclidean distance, we take like one value and another one and we compare them, right? So that's what we do this here. Y pred is compared to yb, the real values. Because it's classification, remember, the function that we will define is cross entropy, which we still need to learn what that means later on. And then from this loss, where we have the error calculation, we do these 3 functions, and that updates the weights. All right, so that's done. And now we're ready, once again, to train our model. Exactly the same thing as before. I think I called the class DLNet, so let's change the name. So DL. All right, so I instantiate the class, and I call it model. That's like the common convention in PyTorch. You always call it the model. And then notice that I link the weights of this model to the optimizer by doing this, right? So you're passing, this is like the connection that says the optimizer will optimize on these things defined as parameters, which are the weights and the biases. Give it the learning rate. Notice here the loss Fn is cross entropy. This is like a very interesting idea from information theory. We'll look at this in a later class. And then we run all of these through the training loop. And there you go, it's training. All right, so yeah, so that's the idea. So we're actually making good progress. So notice it's a bit slower now, right? Because I'm not using the GPU. All right. Right, I'm doing the DLNet. Yeah. Okay, so let's let it run. It's taking a while, actually. How many iterations is it supposed to be? 1,000. See, this is where it's probably better just to switch to the GPU. Do you see what I'm saying? It's taking too long. Let's see if I'm wrong, right? But you saw how slow it was. So I'm going to switch over to T4 GPU. Save. The only problem is I have to rerun all of this again. But okay. You know, Iris only had very few samples, right? It was only 150. Did it give me an error? Okay, it's got these. I didn't install these here. So I don't need Onyx here, so I can just ignore them for now. Because I closed the Colab and then I reopened it. Still taking a bit. Yeah, so it's slower, right? So you can see this now. You know, this is not even like a large data set or anything like that. But as you start adding more architecture, you know, more neurons, more data samples, right? So this, you know, Iris had what? 3. Remember that? And it had 150 samples. And the features were 4. This one has 11. So we have a hidden layer of size 15. We have 2 hidden layers, so you can see it is slower. But essentially the GPU, if done correctly, should be much faster. All right, so we're already up to like 300, so that's good. So we should be done in a second. So while it's processing, just, you know, just to kind of to wrap up, so today we did we looked at creating a deep neural network for Iris. Then we started with the wine quality data set. The wine quality data set, we're going to use that data set for both the classification and the regression problem. In today's class, we focused on the classification problem. We implemented a deep neural network that I'm currently training. And then that means that in the next class on Monday for you guys, we will just look at the regression side of with this data set, right? So study this one really well. Understand, well, you need it for the exam anyway, but understand this implementation really well for the classification case. And that way, when we look at the regression case, you'll see that it's just a few tweaks here and there that we have to make. We have to use a different loss function and so on. All right, so I think on Monday we should be able to finish that, and then after that, I will introduce yet another data set called MNIST, which is the handwritten digits data set. That's images now, so it's going to be even larger, 60,000 samples. The size of an image is 784 features, so you can see how, you know, that's important. And then we're going to build a deep neural network, and I will also hopefully have time to introduce the CNN, all right, which is an even more advanced architecture. All right, this, as I said, study this, please. The exam will be on Wednesday, since you guys asked for that. And yeah, that's it. Please, you have one homework assignment due, I believe, today, right? The perceptron. So please make sure to submit that, and then study for the exam. No homework this week. Yeah. All right. So we're in good. You know, we're doing good, and we should be able to reach transfer learning in about a week for the project. All right, guys, we can stop here, and I'll see you guys next week. And there's the scores. All right, so I'll stop the video here.